The deep dive is back, and today we're going, well, deeper than we've ever gone before. We're going back to the very first fraction of a second of the universe's existence. We're talking about inflation, that almost unbelievable moment of exponential expansion that basically set the stage for everything we see today.
It's a period where the physics gets pretty wild.
It really does. I mean, we think this cosmic stretch was driven by some kind of quantum field, right, or the inflaton, but the energy scale we're talking about here is just staggering. It's way above anything we can model cleanly, often beyond what we call the grand unified theory scale.
Right. And when you're up there, you can't just pull a standard textbook off the shelf. You're working in a framework called effective field theory.
And you're often looking for clues from, the really big ideas.
Exactly. From things like string theory.
Which brings us to the specific model we're diving into. It takes a piece of that high-energy world and plugs it into cosmology. It adds this theoretical term to gravity called the Gauss-Bonnet term, or GB for short.
And this isn't just some random mathematical term they pulled out of a hat. It's a form of higher derivative gravity, and it's something that seems to pop up naturally from things like heterotic string theory. So it has a real theoretical pedigree.
So it's not just a fix, it's a theoretically motivated one.
That's the idea. We're looking at what happens when you couple this thing directly to the inflaton field. Does it solve problems? Or, does it make things worse?
And that's our mission for this deep dive. We're going to put this model through a 3-stage stress test. We want to constrain its 2 main free parameters, the inflaton's mass, which we'll call $, and the strength of this GB coupling, which is beta.
And we're going to hit it from 3 totally different angles.
Right. First, direct observational data from the PLANCK satellite. Then, indirect constraints from the messy period after inflation, the reheating phase. And finally, a purely theoretical check. Does the theory even make sense on a quantum level? A unitarity check.
And you should really listen for this, because here's the spoiler, the big surprise. While the PLANCK data at the beginning seems, well, pretty generous, it leaves a lot of room for the model to work, the other 2 checks. Reheating and unitarity come in later and act like a theoretical guillotine. They just slash that available space, which is a fantastic check on how we build these theories in the first place.
Okay, so let's get into it. Stage 1, inflation and the PLANCK data. So the paper looks at 2 classic potentials for the inflaton. The first is what we call chaotic inflation, where the potential is like a simple parabola.
The simplest model, but one that has some known issues with the data.
Exactly. And the second is Higgs inflation, which, as the name suggests, has a potential that's a bit flatter, sort of mimicking the Higgs field.
And it's important to ask why they're even adding this GB term in the first place. It's because these simpler models, on their own, they just don't quite fit what PLANCK measured. So this non-minimal coupling, this GB term, is an attempt to fix those shortcomings.
It's a patch.
It's a patch, but it's a very sophisticated patch with, a good reason to exist from string theory. It's what physicists do when a simple model breaks.
So to see if the patch works, we look at the 2 big numbers PLANCK gives us. First, the scalar spectral index. This basically tells us if the initial ripples in the universe were the same strength on all scales. PLANCK nailed this down to about 0.968, incredibly precise.
That's an amazing measurement.
And the second number, maybe the more dramatic one, is the tensor to scalar ratio, R. This is huge because it's our only window into primordial gravitational waves from inflation. It tells us how violently space-time was shaken. And the current experimental limit is that R has to be less than 0.07.
Pretty tight. And that leads to the first immediate finding. The Higgs-like model, even with this fancy GB term added, it still doesn't work.
It's out.
It's still strongly disfavored. It just can't quite hit that precise value for LSA that PLANCK measured. So Higgs inflation is still on the ropes.
But this is where the story gets really good for the chaotic model. Because if you take just plain chaotic inflation with no GB term, so what is a 0?
Yeah.
It should be completely ruled out.
Totally. It predicts a value for R that's like over 0.14.
More than double what's allowed. It's dead in the water.
You would think so. But when you switch on the Gauss-Bonnet coupling, even a little bit, it fundamentally changes the game. It acts to sort of dampen the production of those gravitational waves.
So this extra term from string theory basically saves chaotic inflation from being falsified by observation.
That's exactly it. It pulls the predicted R value down, 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 right back into the region that is perfectly compatible with PLANCK. It's a stunning rescue.
Wow. Okay, so a model that was basically ruled out is now a contender again. But what's the catch? Can beta be anything it wants?
No, not at all. This rescue comes at a price. To make it work, you need a very, very tight relationship between the inflate and mass and the coupling.
What do you mean by tight?
I mean, they have to be almost perfectly balanced against each other. If Maillard goes up, Maillard's has to go down in a very specific way. The product of the two, beta times Baller squared, has to equal this ridiculously tiny number, somewhere between 10 to 4 and $10 in Planck units.
So it's not a free lunch.
Yeah.
You save the model, but you have to accept this really fine-tuned condition between your parameters.
Precisely.
Okay, so that's stage one. Direct observation gives us a qualified win. There's a huge space of possibilities, but they're all sitting on this very thin, fine-tuned line. Now for stage two, and this is way more subtle, we're talking about reheating.
Yeah, this is the murky, chaotic period right after inflation ends. The universe is no longer expanding exponentially, but it's not the hot soup of particles we know and love yet.
It's this messy transition phase, and we can't see it directly, so how do we constrain it?
Indirectly. The main tools are things like making sure the total entropy of the universe is conserved. You have to make sure that the universe we see today could have evolved from that post-inflationary state.
So you're basically using bookkeeping to constrain fundamental physics.
In a way, yes. You have to make some assumptions about, how long reheating took, how hot the universe got, the reheating temperature. The authors here model it as a kind of generalized two-step process to cover a lot of bases.
Right, so let's get to the tension. PLA-NCK gave us this huge, fine-tuned parameter space. What does adding the physics of reheating do to that space?
It crushes it. It takes that wide-open field of possibilities and just dramatically shrinks it.
How? What's the mechanism?
It comes back to that scalar spectral index, Schiz or Ban. If you choose a value for your G-beat coupling for a beta law, that's too big. It actually shifts the prediction for a band just enough to push it outside of that super precise window that PLA-NCK measured.
Wait, hang on. How can something that happens after inflation, like reheating, change a number like app that was set during inflation?
That is the beautiful subtlety of it. The exact value of Nisa-Zollars that we observe today depends on when the scales we see left the horizon during inflation. And that depends on the total expansion history of the universe, which includes how long inflation lasted and how long reheating lasted.
So if you change the reheating phase, you change the whole timeline, which ripples backward and changes the prediction for what we should see today.
You got it. It's a powerful chain of reasoning. A large beta messes with the timeline, which messes with the prediction for Nisa-Dollar.
So what does that do to the models? I assume the type 2 quadratic one is in even more trouble.
Oh, yeah. The type of model gets squeezed into this tiny, tiny corner that's in clear tension with the data. But even the survivor, the type I linear model, gets hit hard. The viable region for BSO-Ehlers is now restricted to be, very generally, less than about 1,000.
1,000, but PLA-NCK alone would have let it be much bigger.
Much bigger. So the messy middle phase of the universe turns out to be a much stricter gatekeeper than the initial inflationary phase.
But what's really surprising is what this means for the reheating temperature itself in the models that do work.
Right. The models that survive both checks, they naturally predict incredibly high reheating temperatures. We're talking maybe 10, or even up to 1016 GV.
That's incredibly hot.
It is. It points towards scenarios we call instant preheating, where the infleton just decays almost immediately. And that's fascinating because you need those kinds of high energy scales for other theories like baryogenesis, the reason we have more matter than antimatter.
So we've gone from a vast allowed region to a tiny sliver, all from indirect arguments about entropy. Now let's pivot. Let's leave cosmology for a moment and go to pure quantum field theory. Stage 3, the unitarity check.
Okay, so this is the completely different kind of test.
So in simple terms, what is unitarity and why do we need to check it?
Unitarity is, well, it's a fundamental rule of quantum mechanics. It just says that the total probability of all possible outcomes of any interaction has to add up to 1, 100%.
Seems reasonable.
It is. But in these effective field theories, as you go to higher and higher energies, sometimes the math gives you probabilities that are greater than 1. And that's nonsense. It's a signal that your theory has broken down. It's the theory's self-destruct button.
So the goal is to find at what energy scale our Gauss-Bonnet theory hits that button. How do you calculate that?
The standard way is to look at scattering amplitudes. You calculate the probability of, say, two particles of gravity colliding and scattering off each other.
Yeah.
You see how that probability grows with energy. If it grows too fast, you know you're heading for trouble.
And in this model, for the type I case, the probability grows very, very fast with energy. The breakdown point is tied to the value of beta.
That's right. The bigger beta is, the lower the energy at which the theory breaks. So to make sure the theory is still valid during inflation, which happened at a very high energy, you get a constraint onto beta.
And that constraint is
That beta must be less than about 10 to the power of 10.
10 billion.
Wait, 10 billion.
Yeah. But that's a huge number. That's barely a constraint at all. We just found out from reheating that beta has to be less than 1,000.
And that is the absolute punchline of this entire investigation. The fundamental quantum consistency check, unitarity, gives you an upper limit on beta of $10. But the cosmological requirement from the messy middle phase of the universe gives you a limit of about 103.3 hours.
So the universe itself is putting a much tighter leash on this theory than the underlying quantum mechanics is.
A vastly tighter leash.
Yeah.
It's an amazing example of how cosmology can provide stronger constraints on fundamental physics than a pure particle physics calculation can.
And what about that type 2 model that was already struggling?
Interestingly, it's harder to test with this specific calculation, but all the signs from power counting suggest its high-energy behavior is even worse, that it's sickened, as physicists say. It probably breaks down at an even lower energy, which just adds another reason why it's not the favored model.
Okay, this brings us to one of the original motivations for even studying this. A failed hope, in a way. People were excited about large values of Betafil for a very specific reason, right? It had to do with gravitational waves during reheating.
That was the dream. The idea was that maybe this strong gravity coupling could trigger a huge resonant production of gravitational waves as the insulin was decaying, a process called gravity-mediated preheating. It would have been a totally new way to reheat the universe.
It didn't work. Why not?
Because of the fine-tuning we were forced into back in stage 1. To match the pledal NCK data, we needed that really specific tiny relationship between the influence NAS outgoaler and the coupling of pedal.
The thing that made it a success for inflation.
Exactly. That very same condition that makes inflation work turns around and kills the preheating idea. It suppresses the effective coupling between the inflaton field and the gravitational waves by a factor of about, well, 10,000.
So the coupling just becomes way too weak to do anything interesting.
It's minuscule. The numerical simulations they ran show absolutely no resonant amplification, no fireworks, nothing. So that gravity-mediated preheating mechanism is completely ineffective here. It's a non-starter.
So the model has to rely on normal particle decay to reheat, just like any other model.
Right, and it's such a critical lesson for model building. You have to check your theory across all the cosmic phases. What looks like a great feature during inflation might get completely shut down by the requirements of reheating.
So let's try to synthesize this for everyone. We started with this promising model, scalar Gauss-Bonnet chaotic inflation. The GB coupling, beta, came in like a hero. It saved the chaotic model from being ruled out by Pele and CK.
It did. It damped the gravitational waves perfectly. But then the rest of cosmic history came calling. The requirements of the reheating phase and then the check for unitarity came in and just slashed the parameter space. They forced that hero coupling, Tortolabia, to be much, much smaller than we might have initially thought.
And the really powerful insight here, the main takeaway, seems to be about this hierarchy of constraints. It's that the rules governing the later universe, that messy reheating period, can actually be more restrictive on fundamental high-energy parameters like beta dollars than either our direct observations of the beginning or our checks on the internal quantum logic of the theory.
That's it perfectly. The middle chapter of the story put the tightest constraints on the characters from the beginning.
An amazing result.
It is. And it leaves us with a final thought for you to chew on. Remember that all these powerful constraints from reheating, they relied on some simplified general assumptions about how that messy process works. So the question to ask yourself is this. If we could do a more realistic, more complete analysis with the actual particle physics of the inflaton's decay, would that new level of detail rescue this model and make it perfectly viable? Or would it reveal new tensions that kill it off for good?